Hello and welcome. In this video, we're going to talk about feature scaling. It's one of the key steps in data pre-processing. And as you know, in any analytics project, we allocate roughly 85% of the time in data pre-processing. Feature scaling is an important part of data pre-processing. But what are we going to learn today? We're going to learn all about feature scaling, starting with what is feature scaling? Why do we perform feature scaling? Choosing the appropriate feature scaling. And this is one place where people mostly go wrong. They know a couple of scaling techniques, and they try to force fit only those techniques without realizing what are the consequences of choosing the wrong technique on the right data. So we will spend enough time discussing this. Then we will talk about the advantages and disadvantages of feature scaling. And finally, we will do a hands-on feature scaling in Python. Let's get started. Let's have a look at some data. So we have a very limited data view here, which is relative to 5 features. Let's say this is a company which has collected data about its managers. So we have the age of the manager. We have captured whether the manager is new to the role or not. So there could have been an individual contributor who's been promoted to a managerial profile. In such cases, we have captured it as a 1, otherwise it's a 0. Then we have the team size. Because it's a manager must be responsible for managing a team. So this is a team size which ranges anywhere between 9 to 15 in our case. Then we have the last performance rating of the manager. So it could be anything on the scale of 1 to 5. 1 is the lowest and 5 is the highest. And then we have the sales column, which is relative to the sales performance delivered by this team that's managed by a particular manager. And this is an amount in thousands of dollars. First of all, do you notice that all these variables vary a little bit on the scale? For example, the age is anywhere between 22 years, that's the minimum, to 31 years. This column called new role has only 2 possibilities. Either it's a 0 when the manager is experienced, or it's a 1 when it's a newly promoted employee who has just become a manager. Then we have a variable called team size, which is again fairly range bound. Then we have a rating, which cannot be anything other than a number between 1 to 5. You can't have a rating of 30 here. You can't have a rating of -5 here. It is only going to be between 1 to 5. And then you have a sales figure, which is captured in thousands of dollars. So if you see, the magnitude of these variables differs a lot. For example, we have these values in tens. This is a unit. This is units as well as tens, kind of a mix. And this is something which has values always in units, and this is a value which is in hundreds of thousands. So scaling is essentially about bringing all these variables on the same scale. So we understand feature scaling is about bringing the features on the same comparable scales. But why is this important? Let's understand that. Let's say your management gives you a task to compare the performance of those employees who have recently been promoted to managerial profile. If you see, there are only 2 such cases. And if we concentrate only on these 2 records, this is what we have. So when we talk about comparisons, it's not just one number that we are comparing. We have a number of features here. We have the age, we have the role, we have the team size, we have the rating, as well as sales. One such measure of comparison is always the distance. And which distance is most popular? You're right, the Euclidean distance, which talks about taking the sum of squared differences between the values. Whether you write x2 minus x1 or x1 minus x2, that doesn't make any difference because we are eventually squaring all the values. So if we take a difference between all the features, square them and add them, and take a square root of that, it is known as the Euclidean distance. Let's put these values here. Let's say this is x1 and this is x2. This is y1 and y2 and so on and so forth. This is q1 and this is q2. Let's just plug all these values here. This is what we get. And if we just solve this to the next step, we'll have to just take the differences and square them. So the next step is this. 25 minus 22 is 3. We're squaring and adding. 1 minus 1 is 0. So on and so forth. 75,000 minus 100,000 is negative 25,000. And that's what we're going to square. Like I said, because these are squared differences, you write 100,000 minus 75,000 or 75,000 minus 100,000 would not make a difference. Let's simplify this further. We've got the squared values here. Now, if you notice, which feature seems to be dominating the most here? The one which has the highest magnitude, which was in hundreds of thousands of dollars. Everything else becomes less important. So in a way, we are saying it is not important for us to look at how many people were there in a person's team. All that matters is the sales. Probably that would not be the right way. You're also saying that it does not matter what the last performance rating of the individual was. All that matters would be the sales value. Maybe that's not the right approach. Because of the magnitude, you are giving higher weightage to sales. Everything else is getting negligible importance compared to the sales amount. Let's change the scenario a little bit. What if I say I want to capture these sales, but instead of writing in these units, I would have captured it in hundreds of thousands of dollars because I know this occupies a higher scale. So what if I capture it like this? Now, if I capture it as hundreds of thousands of dollars, it means this represents $100,000 and this represents $75,000. The same number represented in different units. And let's calculate the distances the same way. Now, because the units in which sales values are being measured, you would not see that high an impact. In fact, this becomes the least important feature for you. So you realize how impactful a feature's scale could be in making conclusions? Something that we were considering the most important aspect till now has become the least important aspect. Why? Because we have changed the units in which we are measuring. So don't you think this can lead to wrong decisions or wrong conclusions if we give this kind of data as input to our algorithms? Even if we talk about the unsupervised learning where we do clustering, distances are very important. And some of the algorithms that we learn rely heavily on the distances between the observations. So we need to ensure that the features are on the same scale, unless we have a very specific reason to give higher weightage to a particular feature. The next important question is, should we scale every feature? The answer to that is no, not really. Why? Because if you see features like rating, which has only got a scale of 1 to 5, there's no point scaling this feature. This is already at a minimal scale. But the features like age, team size, and sales would need scaling because if you don't scale these, compared to new role and rating, they will always get higher weightage. Now let's look at the choices. And I know I'm going to talk about a choice which is relatively new for some of you, at least at the time when I'm making this video. So because the third technique mentioned here is not commonly taught in most of the courses, even though it is a very, very important scaling technique. You'll learn that shortly. By the way, if you're watching this video till now and you're liking the way we present things, you may consider subscribing to this channel and share this video with others as well who might benefit. So let's talk about these techniques one by one. The standard scaler, the most common scaling technique, it follows this kind of transformation. So you take a value, subtract the average of the feature, and divide it by the standard deviation of the feature. Every value in a column would be scaled by using the column mean and column standard deviation. And we will discuss its properties on the next slide. Then we have min-max scaler, which takes every single value in a feature, subtracts the minimum value of that column, and divides it by the range, which is nothing but the maximum minus the minimum value. This is another form of scaling. And the last one, which I've mentioned here, is known as the robust scaling. We'll discuss why this is important, but if you see, the scaling is a little different. It is taking a value and instead of mean, it's subtracting the median from that value and dividing by the interquartile range. Now, what is an interquartile range? It's the middle 50% of the data. Essentially, the difference between the 75th percentile of your data and 25th percentile of your data. I hope you get a hint when this kind of scaling would be useful. Let's do a comparison between these three techniques, when to use what. So a standard scaler is particularly useful when you're dealing with classic machine learning algorithms, which are statistical in nature. A lot of tests, a lot of algorithms assume the data to be normally distributed. And this X minus mu by sigma transformation you saw essentially fits the data to a standard normal distribution. Now, what is a standard normal distribution? A normal distribution which has a mean 0 and standard deviation 1. Now, going by the properties of a standard normal distribution, 99.73% of the data lies between plus minus 3 standard deviation. Now, the standard deviation here is 1. 99.73% of the values that you obtain after performing standard scaling would lie between plus or minus 3. Because the standard deviation is 1. So plus minus 3 standard deviations, 3 times the standard deviation is nothing but 3 into 1, which is 3. On the other hand, when do we use min-max scaler? When we do not have any strict assumption about the normality of the data. We don't need the data to be fitting a particular distribution. And the other important piece is that this is going to make the data strictly range bound. It is going to lie strictly between 0 and 1 and can attain both the values. Whereas in case of a standard scaler, 99.73% data is guaranteed to be between plus minus 3. But there could still be 0.27% data which would not lie between plus minus 3. Normal distribution is asymptotic. It doesn't touch the x-axis, you know that. And finally, the most practical scaler, which unfortunately is taught not so commonly in courses, the robust scaler. Most of the times when you're dealing with a real-world data, it is likely to have extreme values. Now, the limitation with standard scaler and min-max scaler is that they are not suitable when you have extreme values. And in such cases, we use robust scaler. Why standard scalar and min-max scalars are not suitable? Let's look at the equation. If you have extreme values, your mean is going to get affected. Mean is affected by the outliers. And so is the case with standard deviation. So if your mean and standard deviation both are affected, this scaling would no longer remain meaningful. Similarly, if you have outliers, the outliers would either be the minimum value or the maximum value, or maybe both in case of your data. So if you're using the extreme values only to perform scaling, how could that be right? And that's where this is free from the central tendency that's affected by the outliers. It is using median, and it's using the middle 50% of the data. If you've seen box plots, you know what is middle 50% of the data. This is not affected by the outliers. And like I said, in real world, most of the data is affected by outliers. Therefore, robust scalar is more practical compared to the other scalars. Once again, robust scalar does not follow any specific range. It tries to accommodate the values as they are, but does not follow any specific range, nor it follows a specific distribution like standard scalar. So it's neither following the distribution like standard scalar, nor it's following a strict range. It's not guaranteed to be between. Now, before we go to the hands-on piece, let's quickly discuss the advantages and disadvantages of scaling. First, the advantages. It helps compare the features a little better. Why? Because when features are on the same scale, they are given equal importance. It helps with faster model convergence. Now, this is something which is a very important aspect when you're dealing with large data sets, huge data sets, and you're trying to apply a complex machine learning model. It will just take forever. In such cases, it is observed that when your features are on comparable scales, the model tends to converge faster. It saves a lot of time and resources. And lastly, for the models which rely on coefficients like linear regression, logistic regression, etc., scaling makes the comparison of coefficients easy. Because the features have been given equal importance, when you compare their coefficients, it's a fair comparison. What are the disadvantages? Loss of feature interpretability. What does it mean? So let's say you have a column called age. Just some time back, we saw it had values ranging between 22 years to 31 years, maybe. It will have some values below zero and some values above zero. Why? Because it is going to fit a standard normal distribution. Half of the data is below zero and half of the data is above zero, which is the mean, because zero is the mean there. How would you interpret the negative age? When somebody says the age of a person is negative 2.5, what does it mean? So this is one disadvantage for people who do not really understand scaling. If somebody doesn't know scaling, would never be able to understand how could an age be a negative value. Information loss. Now, this happens when you try to force scale the features which are already on the right scale. Remember, we dropped a couple of features from scaling scope, like the new role and the rating, which were already scaled. We should not try to scale the features all over again. And third piece is that you need to be carefully knowing the choice of scaling before you apply. Just because scaling is right, it doesn't mean you apply any type of scaling to any data. A lot of times, like I said, people don't know the right scaling technique and they force fit, and without even realizing, they make a mistake. Now it's time for us to move to the hands-on piece where we will show you in detail how scaling is applied in Python. All right, so we are at the Google Colaboratory, and I've already pointed to the data source, which is the same data that I had shown you on slides, the TWI data, which has about 10 rows. But that's sufficient for us to experiment with everything to do with the scaling techniques that we talked about. So to begin with, we are calling all the necessary libraries like NumPy, Pandas, Matplotlib, Seaborn, and we also need these three scalars that we talked about, which are standard scalar, min-max scalar, and robust scalar. These are available in the library called scikit-learn and in the preprocessing module. We are also importing warnings so that we can avoid unnecessary messages. And let's just execute this cell. We will read the data using Pandas read Excel method. And let's quickly check the data. We generally would prefer checking first 5 observations or so, but the data set is so small that I can afford to print the entire data frame here. And you can see this. These are the 5 columns that we had, and these are the values that we had in our data. Let's check the features. So to quickly access the names of the features, we can just do df.columns, and it shows the feature names. It's already visible here as well. But once again, as we discussed, would we want to scale everything? Not really. We would not want to scale the columns like new role and the last performance rating. So we are going to select a subset of the data frame, which contains the features that we need to scale. So these features are the age, team size, and sales. Now we are quickly doing a plot, a visualization to look at the distribution of these variables. How do they look like? What scale do they take before we scale them? And how would they look like after we scale them? That will come later. We are storing these features, the names of these features, to a variable called columns to scale. And then we are just setting up a plot size. This is a value that we can try to adjust depending on how it looks aesthetically. Let me execute this cell. Next, we are running a loop which goes over all the features which are contained in this df sub. And we are creating a visualization which will be 1 row and 3 columns, which means in a single row, I'll see all 3 plots, which will be easier for me to do a comparison. We are doing an I+1 here because plt.subplot does not accept the index 0. It starts plotting the plots from plot 1, plot 2, plot 3. So we have to adjust this. In general, the indexing in Python starts with 0, but in plt.subplot, it does not start with 0, particularly for the plot number. Then we are doing a KDE plot, which will be a density plot, where each of these features will be selected one by one. So what are we saying? Columns to scale df columns. When you do df.columns, it returns you a list-like output. So this columns to scale is a list which contains these 3 features: age, team size, and sales. To a list, if we index something as 0, it would return the first value of that list. We are going to go over all the values one by one. So 0, 1, and 2. How? Through a for loop. And then this is the data frame that we are referring to. We're also doing a fill, which is more of a cosmetic thing, to fill the density plots with a blue color. And we are dynamically adjusting the title as well. We'll type distribution of, which will be a common string, and then it'll keep on taking the name of the feature from the list. We are not interested in seeing the Y ticks, so we have put it as blank. We are more interested in seeing how the values look like on the x-axis. And finally, we are doing a tight layout to ensure these plots are nicely separated. Let me run this and show you the output. So this is how the distribution looks like. You can see we saw age ranging anywhere between 22 to 30 years. It shows more values here because density plot kind of stretches at both the ends, but those are not necessarily the values that are present in your data. Similarly, we saw the team size, and this is the distribution for team size, and these are the sales values. You can see because of the scale that we've chosen, some of these values are nearly overlapping, but we can manage. Now let's also check if any of these features would contain outliers or extreme values. We're not very clear about it through this at least. So to do that, the only change would be in the type of plot. Everything else in the code that I explained would remain the same. Again, we're considering this collection of same features. We are running a loop, and this time we are creating the box plots. Box plots are the easiest visualization tools to detect the presence of outliers. Let's run this. And we don't seem to have outliers. Outliers would typically show up as some points above these whiskers or below these whiskers that you see, but we don't seem to have that. So for now, we don't have outliers, and we can go with the common scalars. But later on in the same example, I'll show you when we have outliers, how do we apply robust scalar? So the syntax is pretty straightforward and standard. We are calling the standard scalar from the sklearn.preprocessing library. We called that earlier in the beginning of the code. We are calling it scalar1, and we have to fit transform this scalar to this data. So that this scaling technique of x minus mu by sigma that you saw is applied to all the features in the subset of the data frame. Let's do this. And once we do this, this gives an output which is in the form of an array. But we are more comfortable working with the data frames, so we can always write an additional line of code which will be transforming this array into the data frame. You have to mention this piece, the exact same piece that's written here, but you have to give it as an input to the pd.dataframe method. And you have to mention the feature names, because when it's a data frame, it would also need feature names. Let's look at how the output comes. So you can see this is the output. You see the difference in this and what we had originally? The features were on a very different scale. So now you can see all these features are on comparable scales. You don't see sales in hundreds of thousands of dollars. You don't see team size as a double-digit number anymore. And you don't see age also as a double-digit number between 22 to 35 or something like that. These are all comparable numbers now. Let's see how would the distribution look like now. So the exact same code I showed you earlier, I'm using this to visualize the scaled output, which is the scaled output. This exact output that we got here, I'm trying to visualize that now. So the difference that you can detect is majority of these values are in the range of -3 to 3, that plus minus 3 standard deviation thing we talked about. Be it age, be it team size, be it the sum of sales, all the features are taking nearly the same scale, -3 to 3 kind of scale, because we have tried to apply the standard scalar. Pretty similar would be the syntax for min-max scalar. We're calling it scalar2, and we are calling the min-max scalar. Again, the same step. So instead of doing it separately, we are doing it in one step only. We are straight away creating a data frame where we are doing a fit transform and choosing the columns to scale. Let's look at the output. Now, if you see, this does not show you negative values. As we discussed on the slides, this leads to an output which is range bound between 0 and 1. So you don't see anything below 0, you don't see anything above 1 here. Let's look at its distribution now. Pretty much the same syntax. Okay, you might be thinking this is a negative 0.5 and negative 0.5, but this is just kind of a density function which stretches, but the values actually in your data are not below 0 or above 1. And now let's look at the mean of our variables here. So we are just calculating the mean of all the features. So far, we realized that we could apply min-max scalar or standard scalar as we didn't have outliers. And these are the mean values that we have. But now what I'm doing is I'm trying to insert some outliers in all the features. And how do I do that? I choose each of these features and at certain locations, which is nothing but the reference to the index value in the data set, I'm trying to force these values, which will override the existing values. So this is the value at index 1. This is the value at index 5. Likewise for sales, index 2, 7, and 9. And for team size, the first value itself, I'm trying to modify. Let me run this and then show you the output after I have modified some values in the data set. First of all, you observe the difference in the means. So the mean earlier for age was 26.4. As a result of these two extreme values that I added, the mean has gone up by 10 years. The team size was just 12.1. It has gone to almost 16 now. And the sales, the average value was around 108,500, which has gone to 154,000. So as a result of these outlier values being added there, you see a shift in all the means. Let's see how these values have been introduced to the data set. So I told you the first value for team size is being modified. You see 50 here now. There was no team in our original data which was beyond 15, but this is now 50. Likewise, there was nobody who was 100 years old, but we inserted this value here and you can see this. Likewise, this 50 here. Similarly, the values for sales. So we never had a value which is 500,000 or 300,000, and we never had a value which is as small as 30. But this is introduced because we kind of force these values. Now, if you look at the box plot, you can imagine the box plot would indicate the presence of outliers. Let's run this. You can see the outliers, the outlier values here, the outlier values here. And for sales, we also had put a value like 30, and that's why you see something here as well. So we have outliers now. And if in this case, we end up directly applying standard scalar or min-max scalar, that will be a big mistake. So which scalar should we apply? The third scalar that we discussed, which is known as the robust scalar. Pretty much the same syntax comes from the same module, and we're just calling it. We are doing a fit transform and storing it back as a data frame. Let me run this. So robust scalar, as we discussed, does not follow any specific distribution, nor is range bound. Let's see how the distribution looks like after we apply robust scalar. So this is how the distribution is. And now the last piece, let's quickly do a comparison between the maximum and minimum values of these different scalars. So we've been storing our outputs always as scaled output 1, 2, and 3. This is for standard scalar, this is for min-max, and this is for robust. Let's see what the maximum value looks like. So in case of the standard scalar, the maximum value that we attain does not exceed a 3 because it cannot go above 3, at least for 99.73% of the cases. Whereas in case of min-max scalar, the maximum value is 1. And in case of robust scalar, there is no restriction like -3 to 3 as we have for standard scalar or 0 to 1 as we have for min-max scalar. So you see different values. And same is the case with the minimum values if we check those. So you can see normal distribution goes on the negative side as well. Min-max scalar would never attain a negative value because it is always between 0 to 1, and robust scalar can take other values. I hope with the help of this video, you got complete clarity on feature scaling, and you'll be able to choose appropriate scaling when the data needs it. Thank you.